Hi, everybody. This is Ms. McClellan here to go over notes 4.2.1 with you. Now, in the previous chapter, we used the idea of similarity in right triangles to identify a relationship between the acute angles and the length of the legs of a right triangle. Now, we don't always just work with the legs of a right triangle. Sometimes we only know the length of the hypotenuse. So where before we could relate our search to slope and tangent, now we will have to deal with some other types of relationships. And our learning goal today, I'll write it in first person. I will be able to use two new trigonometric. Usually people will just say trig. Let me see if I can make this focus better. Ratios called sine and cosine to solve for missing side lengths of a right triangle. Okay, so you may or may not do the warm-up before watching this video, but there's a warm-up that CPM gives, and it's kind of nice. They show a picture of a street in San Francisco. And San Francisco, California is known for having really, really steep roads. And that's partly because it's an earthquake area. And as the faults come together or pull apart, I don't know anything really about how the geometry of plate tectonics, but I think the folds go one on top of the other and it makes these tall hills. Anyway, we want to know how high this girl, Wanisha, climbed. And basically what we're trying to figure out is if we know that she went some distance as walking on the street, like how far she walked, maybe it's a mile. And we know her elevation changed by maybe half a mile. Then maybe we need to figure out how far she went horizontally. And our tangent function, which we learned in chapter 3, can't do it for us. So in order to find out how far she climbed, we need to know more about the relationship between the ratios of sides of a right triangle and the slope angle. So we're going to use two different strategies to determine change in y1 and change in y2 for the sides of this example right triangle. And we're going to sort of start exploring what kind of relationships we can establish. Okay, so we're going to use two different strategies for finding change in y1 and change in y2. And because I know that this is blurry, I'm going to make the numbers really big. So the small triangle has a hypotenuse of 2 and the big triangle has an hypotenuse of 6. The small triangle has a change in x of 1, as in I go over 1 for x, and the big triangle is a change in x of 3. And then I have a 60-degree angle identified for my large triangle. And that's called change in y2, and this is called change in y1. All right, so I need to use two different strategies. So the first strategy I will use to find change in y1, I'll try using the Pythagorean theorem. So that's 1 squared plus change in y 1 squared equals 2 squared. And I know I can do this because it's a right triangle, and for right triangles, you can use the Pythagorean theorem. So that's 1 plus change in y 1 quantity squared equals 4. I subtract 1 from both sides. And that gets me that change in y 1 squared equals 3. And then to solve this, I take the square root of both sides. And I get change in y 1 equals the square root of 3, which is about equal to 1.732. Okay. And then I know that these triangles are similar because they have the same slope. I know they have the same slope because they're going along the same line and they're both right triangles. And because of that, I can use scale factor. So since 2 times 3 is 6, my scale factor k is 3. So I can take change in y1 times 3 equals change in y2, meaning change in y2 equals 3 times root 3, which is about equal to 5.196. Another way that I could do this would be with tangent. I know tan of 60 degrees is going to equal change in y1 over 1. And that means that 1.732 is about equal to change in y1. And then again, I would use the fact that they're similar and a scale factor to find change in y2. So I can either use tangent or I can use Pythagorean theorem. Either works. 2 different strategies. It's tan or Pythagoras. Next, I will calculate, this is part B, the ratios. Change in x1 over hypotenuse and change in x2 over hypotenuse. So change in x1 is 1. And for that triangle, the hypotenuse is 2. And change in x2 is 3. And that hypotenuse is 6. And I notice this gives me 1 over 2. This gives me 3 over 6. And these ratios are actually the same thing. 1/2 is 0.5 and 3 over 6 is 0.5. And these ratios must be equal because the triangles are similar. Okay, we're going to take this information and extrapolate, meaning apply it to this next problem. Determine BC and AC in the triangle below. Show all of our work. So this triangle is a right triangle, and one of the angles is 60 degrees. So I know that this is similar to the triangles in parts A and B because I learned that if I have 2 of the same angles in 2 triangles, then they have angle similarity. So I've got 60 degrees and 90, that's 2 angles. These are similar triangles. So I'm just going to, this is part of my work, claiming that they're similar and justifying that claim. So by angle similarity, this triangle is similar to the ones in parts A and B. And because of that, I can take this triangle and set up my ratios to solve for my missing piece. So I'm trying to solve for BC first. I'll do BC first. I'm going to compare this to the other triangle, which was, I'll do the smaller of my two, which was 2, 1, and then the change in y1 had length √3. So if I want to solve for BC, then I can say BC over 1 is equal to the ratio of their hypotenuses. So BC over 1 is equal to 7 over 2. BC over 1 is equal to 7 over 2. So the length of BC is equal to 3.5. Now I can do AC. AC divided by the square root of 3 is equal to 7 over 2. So AC is equal to 7 times the square root of 3 over 2. You might write this as a decimal, in which case you would take √3 divided by 2 and multiply that by 7. So this might all seem like it's coming from a lot of different places at once, but I promise, hang with me, it's going to make sense. We're talking about ratios. Ratios of similar triangles are equal, and we're going to use that to define two new trig ratios, like similar to tangent. Okay, so 458, let's read it. In the previous problem, we used the ratio that included the hypotenuse of triangle A, B, and C. And there are several ratios that we may have used. One of those is known as the sine ratio. This is the ratio of the length of the side opposite to the acute angle. So that would be √3 for this triangle drawn here, to the length of the hypotenuse, which would be right here. For the triangle shown on the right, sine of 60 degrees is √3 divided by 2, which is equal to about 0.866. This is written as sine of 60 degrees equals √3 over 2. Another ratio comparing the length of the side adjacent to, which means next to, the angle to the length of the hypotenuse is called the cosine ratio, pronounced cosine. For the triangle above, the cosine of 60 degrees is 1/2. Adjacent over hypotenuse, 1 divided by 2, 0.5. And that's written as cosine of 60 degrees equals 1/2. I pause. And I turn to the next page. Now, similar to the tangent ratio, our calculator will actually give us both the sine and cosine ratios for any angle. So if we locate the sine and cosine buttons on your calculator, and you could be using any number of different calculators, but they will, if it's a scientific or above, it will have a sine and a cosine button. And we're going to use those buttons to determine the sine and cosine of 60 degrees. So if I press sine, and then I press 60, it gives me this 0.8660, which I notice hey, that's the same thing as what it was supposed to give me. And cosine gives me 0.5000. I'm using 4 digits after the decimal because that's what's traditional for sine and cosine. Okay, we're going to use a trig ratio to write an equation and solve for a in the diagram below. Does this require the sine or the cosine ratio? Let me think. So if I look at my previous page, sine is the length of the opposite side divided by the hypotenuse. So sine equals no, not just sine. Sine, and then the angle is 23 degrees. So sine of that 23 degrees is equal to, sine is the opposite, ratio of the opposite and the hypotenuse. Yeah, so I need to do sine for this one, a over 15. I need to use sine because I have an angle and an opposite side and the hypotenuse. So where tangent was opposite divided by adjacent, sine is opposite divided by hypotenuse. I'm going to finish solving this. So let's see. I cross multiply. This is 15 sine of 23 equals a. And I put that in my calculator. Okay, and I get a is equal to 5.8610. So I solve it the same way that I solved my tangent problems, but now I'm doing sine. Okay, let's do part C now. Likewise, write an equation and solve for B in the triangle below. Do we need sine or cosine? Okay, so this is my adjacent side. This is my hypotenuse. And where sine was opposite over hypotenuse, cosine is, let me see. Cosine is, let's see. The cosine was 1 over 2, which is adjacent over hypotenuse. So cosine is adjacent over hypotenuse, and sine is opposite over hypotenuse. Okay, what do I have here? Cosine is adjacent. Okay, so I have adjacent and hypotenuse in an angle. So cosine of 37 equals the adjacent leg to that angle, which is B, over the hypotenuse, which is 8. And I know I need cosine because I'm dealing with adjacent and hypotenuse and an angle. All right, let's solve this. Over 1, I cross multiply. I have 8 cosine 37 equals B. I put that in my calculator. I get B equals 6.3891. Nice. That matches the key. Great. Okay. So back to Wanisha. So Wanisha climbed this hill. We don't know how high or how far, but we knew we don't know how high she climbed, and we don't know what horizontal distance she covered, but we know the angle of the hill was 17.5 degrees, and the height of the hill was 100 feet. And we're going to use one of our trig ratios to determine how high she climbed. So we need change in y. Now, change in y is opposite. So we have the opposite and adjacent. No, we don't have adjacent. Haha, we have hypotenuse. So we will use sine. Okay, the equation. Sine of her angle, which I don't know if you can read this because I know it gets really blurry, but it's sine of 17.5 degrees is equal to change in y over 100 feet. I cross multiply. 100 times sine of 17.5 is equal to change in y, which is 30.0706 feet. It doesn't really make sense to use this many decimals. We would say about 30 feet. Who says 30.07 or 06 feet? I don't have a measurement tool that can measure feet to that level of precision. So I'm just going to say about 30 feet. Cool. We know how high she went. 30 feet. Woohoo. Change in elevation of 30 feet. If there's anybody who's 6 feet tall in your class, that's like stacking 5 of them on top of one another. No, 6. No, yeah, 5 of them. That's pretty high. Okay. Next problem, 4-60. For each triangle below, decide which side is the opposite and which is adjacent to the given angle, then determine which of the 3 ratios will help you solve for x. So I actually want to pause here because for me, it would be easier to do these with a graphic organizer, which is the 3rd page of the notes. So I'm going to pause, go to the graphic organizer so that we can get all of our formulas in one place. So let's fill this out. So we've got 4 tools that we've either talked about or used today. The first one that I'm going to write is about the sine ratio. So sine ratio. And let's do a little diagram of what it looks like to use it. So the sine ratio deals with if you're given an angle in a right triangle, the opposite over the hypotenuse. Sine of the angle equals opposite over hypotenuse. And in order to use it, you need right triangle. Always a reference angle. And one part given from the opposite or the hypotenuse leg. So you either need the opposite or the hypotenuse. And whichever one you're given, you should be solving for the other. So like if I want to know the length of the opposite and I have the hypotenuse, I can use sine to find it. If I want to use the length of, if I want to find the length of the hypotenuse and I have the opposite, I can find it. Basically, I can solve this equation if I have one unknown, and the unknown could be any of the following: opposite, hypotenuse, or the angle. We'll learn how to do the angle in a couple sections. Okay, name of tool. The other one that we've used today has been the cosine ratio. And in order to do that, we need the right triangle. And we need a reference angle. And we need to be solving for either the adjacent, not the opposite, because cosine is adjacent, or the hypotenuse. And for a little diagram, if this is the angle, we've got cosine of the angle is equal to adjacent over hypotenuse. Now, sometimes students make a mistake if this angle is up there, so I'm going to also draw this version. The location of the adjacent leg is dependent upon where the angle is. I'll do it for sine as well. If this is where the angle is, then sine is always opposite the angle. So the opposite refers to what's away from the angle. Adjacent refers to what's next to the angle, but not the hypotenuse. The last tool that we actually used so far today has been the Pythagorean theorem. Which is that when given a right triangle, I'll focus. The length of the legs squared, a squared plus b, each squared individually is equal to c squared. And for that, you need a right triangle. And two of the three side lengths. Okay, we didn't use it today, but we talked about it a lot, and that's the tangent ratio. It's a bit of a review. In order to use the tangent ratio, you need a right triangle. And you need a right triangle, a reference angle, and either the opposite or the adjacent leg should be given, and you'll be solving for whichever one is not given. So for a diagram, right triangle, angle, opposite, adjacent. Tan of that angle would equal opposite over adjacent, period. And then up here, up top of this graphic organizer, you have a little diagram to sort of summarize everything. It also says SOHCAHTOA right here, SOHCAHTOA, which is something that helps some students remember what ratio goes with what. Sine, so sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. TOA, tangent, opposite over adjacent. All right, I'm going to use this summary to finish the last problem from section 4.2.1. So I'll reread it. For each triangle below, decide which side is opposite and which is adjacent to the given acute angle, period. Then determine which of the three trig ratios will help you solve for x. So I'm going to do the first piece of instruction first. My angle is here. This is opposite. And this is adjacent. My angle is here. This is opposite. And this is adjacent. My angle is here. This is opposite. This is adjacent. My angle is here. This is opposite. This is adjacent. My angle is here. I go across. This is opposite. This is adjacent. My angle is here. This is opposite. And this is adjacent. Notice my adjacent side is never by hypotenuse. And opposite, to find the opposite side, I always go across from the angle. Okay. So for this one, because I'm dealing with my adjacent and my hypotenuse, I'm going to use cosine, adjacent over hypotenuse. So cosine of my angle, cosine of 17 equals 3 over x. Next problem. I have opposite and hypotenuse. That's sine. Sine of the angle is 25 degrees is x over 9. The next problem, I have opposite and adjacent. Well, that's tangent. So tan of 45 is equal to x over 5. Next problem. I have opposite and adjacent. That's tangent again, because I don't have hypotenuse. So tan of 62 equals to 5 over x. Let me focus again. Next problem. I have, oh, I mislabeled this one. Oops. This is opposite and hypotenuse, not opposite and adjacent. It's hypotenuse because that's the longest leg. So, I mean the longest side. So I have opposite and hypotenuse, meaning I'll be doing sine. So sine of 34 is equal to 13 over x. Last one, I have opposite. No, I don't have opposite because I'm not trying to find any information for that leg. So I have adjacent and hypotenuse. So that's cosine. So I have cosine of 20 degrees equals x over 10. Now I have my equations and I will solve them. To solve this one, I multiply both sides by x, and then I'll be dividing by cosine 17. So I'm just cross multiplying and divide. So I have x times cosine of 17 equals 3 times 1, which is just 3. Now to solve for x, I divide both sides by cosine of 17. So I put in my calculator 3 over cosine of 17, and I get x is equal to 3.1371. Next problem. I cross multiply, so I have x times 1, which is just x, equals 9 times sine of 25. X is already alone, so I just plug that straight into my calculator, and I get x is equal to 3.8036. Next problem. I cross multiply. I get x times 1 is x equals 5 times tan of 45. I throw that in my calculator and I get x equals 5. I'm using trig, so I'll do 4 decimals, but honestly, I'm sure many teachers would be like, hey, why are you putting 4 decimals after 5? The number is 5, exactly. And I would agree with them. I'm just doing this to be consistent with the other problems. Next problem. I cross multiply. I have 5 times 1, which is just 5, equals x times tan of 62. X is not alone yet. I need to divide both sides by tan of 62. This side it cancels. X is equal to 5 over tan of 62. I put that in my calculator and I get 2.6585. Next problem. I cross multiply. I have 13 times 1, which is just 13, equals x times sine of 34. I divide both sides by sine of 34 because I want to get x alone. On my right-hand side, it cancels. On my left-hand side, I have 13 over sine of 34. And that's what I put in my calculator to get. I think I did this problem wrong when I made my key, so I actually have to use my calculator for real. So just a moment, I'm gonna type in 13 over sine of 34 on my calculator. And that gets me 23.2478. And I just have to make a little note to myself. Fix part E. Okay, last problem. I have cosine of 20 equals 10 x over 10. I cross multiply, I get x times 1, which is just x, equals 10 times cosine of 20 degrees. I plug that in the calculator and I get 9.3970. Last problem is done, everybody. Yay. Okay. I hope you do your practice. I hope you have a beautiful day, and I'll see you next time. Thanks, everybody. Bye.